Hi there, this is Dr. John, your physics and math professor, and today we're continuing our series in transformations. Previously, in a couple of videos, we looked at different types of translations. Remember, the word translation is a little bit unusual. We don't tend to use that in our English language the way that it's used here, but just think of the word transit. Public transit, like a bus or a subway, which moves you from one location to another but keeps your shape the same. That's what a translation is. You can actually use that word in English saying, I'm being translated, or I'm translating this box from this place to this place. It's a valid use of the English word. And what we did is we translated different functions to the right and the left and up and down. These are called horizontal translations. These are called vertical translations, but the shape stayed the same. Now we're going to be looking at stretches or squeezes. Stretches and squeezes are sort of the same thing, as well as reflections, which are going to change the shape of your object. So here I have drawn a sine curve, very simple sine curve from 0 to 2 pi. And what I'm going to do is I'm going to say, what if I wanted to take this sine curve and stretch it in the y direction? As if this whole surface here is flexible and you can just stretch it out, but this line here, the x-axis, stays solid. So we're just sort of, whatever this is here, it's stretching upward. Whatever this is here, it's stretching downward. Well, what I would have to do is just take whatever y value there is here and multiply it by some factor. So here I've written out this y is equal to sine x. Let me just erase a little bit, give myself a little bit more space here. Y is equal to sine x. So this would be what I have here. What if I wanted to say multiply everything by 2? Well, what if I just put a 2 in front of there? So whatever value I have here for y, let's say I have the value of 1. Well, that value now would become 2. If the value is 0, it would still be 0, because you're just multiplying by 2. If the value is minus 1, it's minus 1, minus 2, way down here. If it's somewhere over here and it's a half, then it's going to be 1. So it's going to be lifted up to there. So the entire thing now is going to be stretched something like that nature. Very, very simple. We're just taking this whole thing and stretching it like this. It's called a vertical stretch. And of course, if you wanted to make this a 1/2 instead of a 2, we could validly do that as well. Let's do that for another one here. Y is equal to 1/2 sine x. I'm going to use a different color for that. Now, if this takes everything and multiplies it by 2, every y value, 1/2 here would just multiply this by 1/2. So instead of being 1, it would be 1/2. The zeros would still be zeros because you're multiplying a 0 by a 1/2. This would be a minus 1/2 right there. So the graph now would be something like this. I'm getting a little bit crowded, getting a lot of things on the graph here, but you can sort of see what's happening here. This is called a vertical stretch, up and down stretch. Remember, a vertical, it's like a basketball player. They jump high. In other words, they have a vertical. They can go very high vertically. So this is called a vertical stretch. You could also think of this as a vertical stretch, even though it's a vertical squeeze. You're squeezing it. But we don't want to use a different word for that. So we'll just use the same word, saying a stretch. It's like a fractional stretch, if you want to do that. Some people will call this a squeeze. Now, what would happen if we make this number in front of here negative? I'm just going to write one more in here. Y is equal to minus 1 sine x. And I'll use a different color again. Maybe this bright blue. So here we have, just think of whatever value you have for sine, I'm going to multiply by minus 1. Obviously, if you make this yellow line, if you make this fraction smaller and smaller, you're going to get closer and closer to the line here. So then it sort of makes sense. If you make it negative, it's going to start going down. So if you multiply this function here by minus 1, just think about it for a second. This value over here, which was 1, you're going to multiply that whole thing, the whole y, the whole sine function by minus 1. This is going to go over to here. The 0 values will stay 0, because remember, we're stretching it like this, but it's sort of attached at the x-axis. So it's going to be minus 1. This one is going to be plus 1. So you're going to have a form something like this. It's going to keep going, of course. Notice how this blue one is sort of a reflection of the purple one. That purple one might not be as visible. Let me just make it, add some black to the purple here, so it becomes more distinct from the blue one. So if you take this one over here, the original sine function, multiply it by minus 1, you actually get that flipped over here and onto the negative side. Or you could think of that as if the x-axis is a mirror and you're taking this function here and reflecting it in the x-axis or through the x-axis or over the x-axis. People will use various words for that. and it's a reflection like the x-axis is a mirror. So putting a minus sign here in front of the sign like this, in front of the function itself, or if I write out the whole thing, so if your function is like this, y is equal to f of x, if you put a minus sign in front of that whole thing, you're now going to reflect it in the x-axis. And of course, the same thing applies to this green one over here. I'm going to use green again. If you made this number -2 instead, you're going to reflect it and stretch it. So you're going to have something like this. You're going to take this one here, stretching this blue one, or stretching it up here and then reflecting it. You can go either way. You can do the stretch first and then reflect, or you can just think of this as a stretch in -2, a stretch of -2. And these things here, the stretches, or the stretches up here and the reflections, really can be done together as a team, because just think of the reflection in the x-axis as being a negative stretch. So whatever you would multiply the y value by, you're going to multiply that by a negative value, and it's going to end up over here. One more thing that I wanted you to see in this, and I'm just going to erase a couple of things here. So let's say we want to take this 2 and move it to this side and associate it with the y is equal to sine x, just like that. We did this previously with the translations. Remember, we had something like this, y is equal to sine x plus 2. We could rewrite this as y minus 2 is equal to sine x, because we're going to need this later on. I wanted to show you how you can do this, because this is a vertical lift, but if we associate it with over here, it becomes negative. That's because when we want to do horizontal translations, we're going to have to associate it directly with the x here, because we can't move it to the other side like we did here. And we wanted to show you the same thing here. We tend not to write it like this. We tend to write the stretches, the vertical stretches right here, because it's easier to visualize. But if we put it over here, it's perfectly valid. But in this case, notice this here is actually a stretch in the y by 2, because we need to make the y twice as big to get the same value of x over here. Because the x values don't shift, but the y values we're going to have to make twice as big to get the same x values. So this is another way of visualizing, and we're going to need that when we do the stretches and the reflections associated directly with the x. So I've shown you this here. Let me just draw another one up here. I'm going to draw another 1 or 2 up here, and just give you an idea of how to do this in a practical sense. Okay, I'm back. I've drawn a couple of shapes for you. I've drawn this unusual shape over here. And then here I've drawn a root of x function. Notice it's got a couple of points. Obviously it has 0, 0. It has 1, 1. It has 4, 2. So if you make x equals 4, you take the square root, you get 2. So we're going to do a couple of stretches and or reflections on this. So first of all, what if we multiply everything here, all of this function, all of the y function, the dependent variable, the y variable, by 2. So to multiply this by 2, what we would have then is this 1 becomes a 2 over there, the y becomes a 2, this 2 becomes a 4, so a 3, 4, it's going to be somewhere over here. So we're going to have this new shape. Remember, all you need to do is draw a couple of pivotal points, and you can copy the original shape. Now in this case it's stretched, so you have to be a little bit careful because it's stretched. It's not, when it was translated, we kept the shape exactly the same. Now we're stretching it, squeezing it, reflecting it, doing a variety of things to it. So this one over here is 2 root 2. That's a very simple stretch. Now what if we did that stretch -1? We did a -1 stretch. Well, we do the same thing. The x variable becomes the same, but what we're doing now is we're taking the y variable, which is 1, which is all of this, root of x, or right here, root of x, and multiplying it by -1. So we're going to have this point over here now. This is now 1 minus 1. The x value stays the same, the y changes. This one over here as well. X stays the same, and y changes. So we're now going to become doot, -1 minus 2. So right over here, it's 4 minus 2. So to draw that, we're going to do something like this. Now notice we've taken this thing here, the original function, and reflected it in the x-axis, or through the x-axis, or over the x-axis, however you want, however your teacher describes it. And that would be putting this -1 over here. Of course, you could put this -1 over here. That would still be a reflection. You could put this and make this a 1/2. you could make that a -1. It's still a reflection. The minus sign stays the same, but here you'd have to realize you're doubling the y. If you're going to move this to the other side, -1/2, let me use a different color again here. This is, of course, it's a reflection, and then it's a right there. So it's going to be between those two. So it's going to be, or you take all the y values here and multiply by -1/2. So you take 1 by -1/2, you get that. Multiply 2 by -1/2, you get -1 right there. Now you could also put this over here. What would you get? -2y equals root of x. So if you're putting this in this form, the y is going to have to be 1/2 of what it was before, because the x values, you want to keep the x values the same. So you're going to have to, but you also have to make it minus. So it takes a little bit of extra thinking. In this case, you would take every y value and multiply it by -1/2. Sort of like, just like you would do here, by -1/2. So here's a couple of illustrations for you. Let me go over here and do this one. I'm going to take this box and do some stretches on it and reflection on it as well. So I'm going to write out the formula. I'm going to erase this just to give me a little room to work. All right, we're going to come back and we're going to work on this shape now. It's actually a trapezoid, if you care. And I've written this saying the original function, I'm going to call this f of x. Now, no, really, I shouldn't probably use the function notation because this is not a function. If you remember, the vertical line test says that if you draw a vertical line anywhere where the function is, and there's more than one points that intersect that, like right here and here, then it's not a function because it doesn't pass the vertical line test. Or another way to think about it is the x components here are called the independent variable. It's the variable that doesn't depend on anything else. But the y variable is called the dependent variable. Dependent variable, which means that y has to rely upon x. If you give me an x, I need to get an exact single, only one y value, or no y value at all if it's not defined there. If the function's not, if I did this x equals 6, obviously there's no y value because the function isn't over there. But for any one single x value where the function exists, there needs to be one specific and only one y value because it has to be dependent upon x here. In this case, it's not purely dependent upon x because there's two different y values. So that's just a little bit of an aside, but I still use the f notation like this just for clarity so that we can see that clearly. Don't need this right now. So let's say we wanted to take this thing, this trapezoid, this function or this relation, it's really a relation, and multiply it by -2. What's that going to be? Well, from what we talked about before, it's going to be a stretch. It's going to be a stretch of 2, but it's also going to be a reflection in the x-axis because stretches and reflections can be taken together. So this would be a negative stretch, the minus, a negative stretch. So I've taken each of these points here and written them out over here. So this first one here is 0, -1, and then this one here is 1, 1, and then this one over here is 5, -1, and this one is 4, 1. I wrote them down wrong before, I just fixed that for you right here. So these are the points that are on our original function, on our original relation. What we want to do is we want to do something to them. Every y value, the x values have to stay the same. Every y value, though, has to be multiplied by -2. So the x value stays the same. So here we just write the x value, and then the y value, we're going to go -2 times y. That's all you have to do. You can do this on here. You can actually take this, stretch it. So that means this point would go to here, and then flip it. You can do that step by step. It's going to take you a little while on the more complicated functions or relations. Or you can just do this, which makes it a lot simpler. So every x value stays the same. So it's still 0, it's still 1, it's still 4, it's still 5. And the y values we multiply by -2. So this now becomes 2. This becomes -2. This becomes -2 as well. And this becomes +2. So I'm going to just erase some of this so I have a little bit of room to work. And then I'm going to sketch these values out for you. And let's use a bright red color for that. So we're going to start off with 0, 2. 0, the x value, and this is 2. So does that make sense? We're taking this thing here, we're flipping it over to here and then stretching it. Or we're stretching it and flipping it or reflecting it. So that sort of makes sense for that one. So this is 1 -2. This is 1, and now it's going to be -2. So it's over there. This one's going to be 4, that's over here, and then minus 2. So make a dotted line over there. Get it over there. 5, 2. So 5, 1, 2. Now let's connect this together. Notice the shape has changed a little bit. However, if you can get the corner pieces, like we did here, draw them in, and then realize, oh, it's a reflection, sketch it in, it'll make quite a bit of sense to you, because you'll notice that this is a reflection and it's a stretch as well. So hopefully this method here, this mathematical method, helps you. We're going to go on. We're going to do stretches and reflections this way as well. We just worked on them in this way. The next video we're going to do this way, and then I'm going to do a bunch of examples for you. So like and subscribe, and I will see you in the next video. Bye-bye.